So in the last class, we were discussing classes, right? So let us continue the discussion and let us see the physical meaning of what do you mean by class? Physical interpretation. So by now, if you have worked out classes for NH3 molecule and C4V molecule, which we were discussing in the previous class, so if you have worked out the classes for these two molecules, you must have realized that classes are the group elements that are equivalent in nature. Intuitively, I must say at this point, they belong to one class, right? So for example, C3 and C3 square, they seem equivalent and then they belong to same class. 3 sigma V's of NH3, they belong to one class. So what do you mean by equivalent symmetry operations? So let us see. Because if we can identify equivalent symmetry operations, we can simply group this equivalent symmetry operations in one class and we don't have to actually calculate all the similarity transformations for individual group element, right? That will be easier. So equivalent symmetry operations are those operations which can be transformed. I'll give you two definitions for this. Into each other by a third operation in the group. So what do I mean by saying that? Let's say if we are considering NH3 molecule, the point group is C3V. So C3 and C3 square are equivalent symmetry operations. That is, effect of C3 or effect of C3 square can be interconverted between each other by a third symmetry element. So let us, without wasting time, let us see what do I mean by that. Let me write down NH3, 1, 2, 3. So let's operate C3 on this and we will also operate C3 square. Okay, so here C3 square. So C3 anti-clockwise will give you the 3 goes to 1, so 3, 1, 2, and C3 square will give you 3 comes here, right? 3, 2, 1. Now these two operations must be related by a third symmetry element. So let's say if I want to go from here to here, what symmetry operation I can use so that I can call these equivalent. Can you find out one? So if I do, so I can say that this is C3. In this case, actually, this is the same, but these two are basically the effect of the two are still interrelated by an element in the group. Similarly, here also I can go by, so this will be by C3 square, right? Yeah, and this will be by C3. Right, so idea is basically that the two symmetry operations are equivalent if the result of the two operations can be interconverted into each other. Okay, it can be by a third element or by basically one of the elements of the group. In other words, we can also say that, let me write down the exact definition. Operations in a class can be interconverted by changing the access system. We will see an example of this. Through application of some symmetry operation of the group. So let us consider C4V point group. So what I'm saying is operation in a class can be interconverted by changing the access system through application of some symmetry operation of the group. So the meaning is, so let us consider C4 and C4 cube, which belong to same class. We should have all worked out by now. So the effect of let's take the coordinate system. Okay, so x, y minus x minus y. Okay, this is the axis system. Axis system I would call as A. Okay, now if I do a C4 operation onto xy, C4z, my x is along z, right? So what happens to x? X goes to anti-clockwise, so x moves to y and y moves to minus x, right? This is the effect of this particular operation. Now similarly, let's say what is the effect of C4 cube on xy? C4 cube will be 270-degree rotation, right? So x goes to minus y and y goes to x. Okay, now let us say that if we change the axis system so that by one of the elements, which is sigma d1, this is the plane sigma d1. Sigma d1 is part of this C4V group. So if we change the axis system, we go to y x minus y minus x, right? Now in this, so let me name it as axis system B. Now in this new axis system, which is obtained by application of one of the group elements, let us apply this C4 operation on xy again. So now if I do onto xy, what do I get? So again I'm doing x anti-clockwise rotation, so x moves to minus y and my y goes to x. Now if I do C4 cube on xy, what do I have? So x moves here, that is y, and y moves to minus x, right? Now you see that the effect of C4 was earlier y minus x, now effect of C4 is minus yx. So the effect of C4 and C4 cube are interconverted by changing the axis system, and the axis system is changed by one of the symmetry elements of the group. So what I'm saying over here is operations in a class can be interconverted. So operations in a class can be interconverted. So operations in the class can be interconverted by changing the axis system from A to B through application of some other symmetry element, which is sigma d1 here. Okay, so this should be very clear. This is the physical significance, because basically what we are trying to say is that when I'm fixing certain elements in a class, that means their effect is interconverted. So it's like changing the axis system and doing the same operation again. So that means, so if C4 is doing certain operation in one axis system and C4 is doing certain other operation in another axis system, then C4 cube should also give me the same result as the previous axis system or the one of the axis system. So the idea is that if we change the axis system, the two symmetry operations change their result, and then they are called as equivalent symmetry operations, and thus they are classified into same class. Now we have understood the physical significance, we know how to classify, and now we will see later that why this is so important, why finding elements which belong to one particular class is so important. That we will see in matrix representation, but that will come maybe in one or two lectures later. So this finishes the discussion for subgroup and class. The next important topic is matrix representation of symmetry operations. These are operators, so all operators by definition can be written as a matrix representation if we know the proper basis sets. So let's work it out. Let's see. Let us consider coordinate system x, y, z, and let's say how a point x, y, z undergo transformation due to these symmetry operations. So let's first consider for identity E. Okay. So let's say we are trying to find a matrix representation for E. So this is the matrix which we do not know. Okay. This is the matrix. Now initial coordinates of the system are x1, y, or of a point are x1, y1, z1. This is the initial location of the point, and this is the final location, new location we can say. Now new location in case of identity will not be different, right? It will be same as x1, y1, z1 because identity operation does not change anything in the molecule or to the point. So that means E should be a unit matrix of order 3 cross 3, right? So that is very easy to see. Now if we do this multiplication, this is a 3 cross 3 matrix, and if we multiply x1, y1, z1, which is 3 cross 1, so what we will get is a 3 cross 1 matrix, right? And we all know how to multiply here matrix, right? So x1 multiplies with 1 plus y1 into 0 plus z1 into 0, which will give you first element here x1. Similarly, x1 into 0 plus y1 into 1 plus z1 into 0 will give you y1. x1 into 0 plus y1 into 0 plus z1 into 1 will give you z1. So that's how you will determine matrix representation for E. So let us look at other symmetry operation. Next in the line is, let's start with the easier ones first, and then we will move to the complex ones. So for reflection, let's say sigma. Okay. So again, let's write down the unknown one as question mark. The initial, let's consider this as sigma xy maybe. Okay. We have to consider one plane, so you can consider any plane. So if we have x1, y1, z1, the initial point will move to, because x1 and y1 would be lying on sigma xy, so they will not change their locations, so they will be same. Then z1 will move to minus z1. Z1 will go to minus z1, right? So that means what do I have as matrix for sigma xy? because x1 and y1 are not changing anything, they will be 1 and 1 at the diagonal, and since z is going into minus sign, you can write z as negative, right? Similarly, you can write for sigma yz, this will be minus 1 0 0 0 1 0 0 0 1, and for sigma xz, it will be 1 0 0 0 minus 1 0 0 0 1, right? So this is easy to see. Reflection is easy. Now also look at inversion. So in an inversion operation, what happens to x, y, z? I matrix. X goes to minus x, y goes to minus y, z goes to minus z, right? So this implies I matrix is nothing but negative unitary. This should also be very clear. There is no confusion in this, right? So now let us look at where we need to do some calculations for rotation. So let's consider C2Z rotation, where Z is collinear because it will be easier to see. So C2Z rotation on x1, y1, z1 gives rise to, so now x1 will move to x2, y1 will move to y2, z1 will remain at z1. So what do I mean? I mean, if this is x, y, z, and we have a point in plane which is x1, y1, z1, which can be represented like this, then I'm moving to a certain point in space, which is by application of C2z, which is now defined with the coordinate as x2, y2, z1. Okay, my height does not change. So if I'm fixing my z1, I can also reduce this to a 2D problem where I can say that x1 by application of C2z matrix, my x1, y1 is actually changing to x2, y2. So this is only for the solving it a little easily so that we are converting into a 2D problem. So let's see what it means. We have x, y, x1, y1 moves to x2, y2. Let's call this angle as phi and this angle as theta, and let's call the length of this point or distance of this point from origin as r, which remains unchanged because we are only moving in this direction. So this is my rotation, right? So if we want to write now x2, y2 in terms of x1, y1, how do I write? So let's see, x1 can be written as r cos phi and y1 can be written as r sine phi, right? This is the basic trigonometry. Now let's say if we are trying to write x2 in those terms, x2 will be equal to r cos theta plus phi, right? Because that is the total angle, theta plus phi. So x2 can be written as r cos theta plus phi, and y2 can be written as r sine theta plus phi, right? So now let's try to expand this. X2 is nothing but r cos theta cos phi minus, we can say r sine theta sine phi, right? That's my expansion for cos theta plus phi. Okay, so now I know that r cos phi is x1 and r sine phi is y1. So I can write x2 as x1 cos theta minus y1 sine theta. So similarly, if you expand y2 sine theta plus phi, what you will get is x1 sine theta plus y1 cos theta. So now if I write this in matrix form, what do I get? So in matrix form, the above equation can be written as cos theta minus sine theta, and we have sine theta cos theta into x1 y1, which gives me x2 y2. Okay, so now again introducing the z-axis in the system, which is not changing. So we can say this implies that cos theta minus sine theta 0, sine theta cos theta 0, 0, 0, 1. Right, I'm only extending the whole thing into third dimension, which is z, which does not change. So notice that I'm writing z1 as z1, right? y1 goes to y2, x1 goes to x2, whereas z1 remains as z1. Okay, so that means this implies that this particular matrix is my representation for C2Z. Now I can take any angle or CNZ, right? This is not, we have not explicitly said any angle here. So this is for CNZ. Let me also correct it in the previous one here. So let's say this is CNZ. All right. So now if I want for C2Z, what I will have to do is my theta will be 180 degree, right? So accordingly, the values of cos theta and sin theta will be placed here, and that will be the matrix for C2Z. Similarly, if I want C3Z, my angle will be now 2 pi by 3, right? And then if it's C4Z, it will be 2 pi by 4, and so on and so forth. So you can easily calculate rotation matrix or matrix representation for any kind of rotation now. Okay. Now next is for improper rotation, which is SNZ. So we all know that improper rotation SNZ can be written in terms of CNZ into sigma xy, right? So sigma xy, because that sigma is perpendicular to CNZ, so that has to be very clear. If we are taking our rotation axis along z axis, then the sigma has to be the perpendicular plane. Now, if we can obtain this matrix easily, because we know that the matrix representation for this as well as this. So let's just multiply the two matrices. So we have cos theta minus sine theta 0, sine theta cos theta 0, and we have x and y unchanged, and z goes to minus z, right? So the only difference we will have is that we will have rest everything same, and instead of plus 1 over here, we will have, the only difference is instead of plus 1 over here, we will have minus 1, which defines that now z1 actually goes to minus z1. Okay, for improper rotation. Okay, and the x1 y1 will still go to x2 y2, whereas z1 will go to minus z1. That is the meaning of improper rotation. Okay, so that should be very, very clear. So if that is clear, we will move to how to write matrix representation. In next class, we will see how to write matrix representation for various point groups. Okay, so that's all for today. So thank you.